Yeah, so let us continue with the renormalization of the electroweak standard model. The last time we discussed a few preliminary remarks and we went through the renormalization of QED, quantum electrodynamics, in detail, setting up all the necessary steps and building blocks in order to have a consistent renormalization picture and renormalization procedure, including in particular the counter terms and the definition of the renormalization scheme, which gives us, let's say, prescriptions for how to compute and how to evaluate the renormalization constants and the counter terms. And now we will do the same thing for the standard model. It is the same structure and the same order of steps that we need to take, but each step is a little bit more involved. And so we will start with the renormalization transformation, which then produces a bare Lagrangian and a counter term Lagrangian, from which we can rid of counter term Feynman rules. The counter term Feynman rules then enter into Green's functions, and we can evaluate how they enter, and then we set up a renormalization scheme where we require on-shell conditions for the particular Green functions we choose, and then we can evaluate the renormalization constants, and then we also have a basis for doing higher order calculations in the electroweak standard model. And probably today we will not do all those steps, but a variety of them, as we will see. So let us begin. Can you see that? So we start with the Lagrangian L classical expressed in terms of physical fields and parameters. Which are in particular the parameters, the gauge coupling for QED, E, then the masses MW, Z, and Higgs for the bosonic electroweak sector and electroweak symmetry breaking, the tedpole parameter corresponding to the vacuum and vacuum expectation value, and in the fermion sector we have all the fermion masses, and as we said, we have only one generation. Therefore, there is no CKM matrix and there is no mixing between the fermions. And among the fields, we have, of course, the photon, the ZW plus minus fields. We have the Higgs fields and the Goldstone boson fields, which are unphysical. And we have, of course, the fermion fields, F, as I will call them, for fermion, quarks and lepton fields, left and right-handed. And we have unphysical ghost fields. We will actually not really discuss the ghost fields in detail here, because we will mainly skip the unphysical sector. So let us start maybe with the bosonic sector, which is the sector involving the gauge bosons and the Higgs bosons and the associated parameters. So there we construct bare fields and parameters. In the following way. So we define a bare gauge coupling E bare as E plus delta E, or equivalently ZE times E, and then the ZE is given by 1 plus delta ZE. This is again this chalk which cannot be deleted. Well. Okay, then for the masses we have M square W Z Higgs bare is given as M square W Z Higgs plus delta M square W Z Higgs, and the tadpole T bare is equal to T plus delta T, where in calculations we set the renormalized tadpole to 0, which means that our tree-level vacuum expectation value is chosen correctly, such that we expand around the tree-level minimum, and at higher orders we will do something appropriate with a renormalization constant delta T, and that is something that we have to choose later on as part of our renormalization conditions. So this is the transformation for the parameters entering the bosonic sector, and then we have also the fields in the bosonic sector. Namely, there is the photon NZ. There is given by this square root of Z matrix times AZ. And so sorry about this, I do not introduce some particular symbol for this Z. It is just Z, and so of course don't get confused between the different appearances of Z, but it becomes clearer if we write the matrix elements. So this is a matrix which is 1 plus, or let's say unit matrix, plus a matrix 1/2 delta Z AA delta Z AZ delta Z ZA and delta Z ZZ, and with those indices it becomes unambiguous what we are talking about, times AZ. Okay, so these are the renormalized fields for the photon NZ boson. This is the renormalization constant matrix, and it is a matrix in the 2x2 space between the photon and Z, and it is an off-diagonal matrix. We discussed last time how it is connected to the symmetric phase of the standard model, expressed in terms of the original U1 and SU2 gauge fields, but here we just use this general 2x2 renormalization transformation matrix. And those, between those four Z factor entries, there would be some relationship, so the divergences of the four are not all independent. That is what we discussed the last time, but anyway, we keep them as independent, and in particular we can choose the finite parts later on with four independent conditions. Then we have the W plus minus. There is given by square root of ZW times W plus minus. Higgs field there is given by square root of ZH times H, and the Goldstone bosons 0 and plus minus are given by Z factor of Goldstone 0 and plus minus times themselves. Okay, so this is the transformation, and that would be applied onto the classical Lagrangian to obtain a bare Lagrangian, and that will be evaluated later on. Let us next specify the transformation in the fermionic sector. There is less, so the quantities are, as we already said, the masses and the fermion fields. And in contrast to QED, the fermion fields left and right-handed behave independently, because we have parity violation in the weak interactions, and the fundamental gauge interactions act differently on the left-handed and the right-handed fermions. And from Lorentz structure, left-handed fermions are independent Lorentz objects, right-handed fermions are independent Lorentz objects, and therefore they do not renormalize in the same way, but they renormalize independently. And in QED, however, because of parity conservation, left and right-handed fermions do not have to distinguish, so that is a new feature here. So therefore,
طبعا احنا شرحنا لماذا الليفت والرايت فيرميون هنا يعني يحصل لها سيبريشن، لانه نحن نتكلم عن تفاعلات عميقه، والتفاعلات العميقه تجعل الكتل مختلفه، وبالتالي الخواص المغناطيسية هي التي تفعل ذلك. وحتى بالنسبة للزي، بالرغم أن هناك خواص كهربائية، مجال كهربائي وخواص مغناطيسية، مجال مغناطيسي مع بعض، لكن في النهاية يعني هذا النزاع يكون السيطرة، يعني ستذهب زي إلى محل السيطرة. ولكن حتى المجال الكهربائي أيضا لديه خاصيتين، أو عبارة عن معادلة اللي هو المعادلة الاستمرارية أيضا يدخل في هذا الأمر. لكن الخواص المغناطيسية بالنسبة للدبليو طبعا تكون واضحة جدا جدا، لهذا يعني ظهرت هذه الأمور.
First of all, the mass mf bare is given as mf plus delta mf, and for the fields, the fermion field bare is decomposed into left and right-handed, and they transform independently, and so that can be written as square root of zfl times a left-handed projector plus square root of zfr times a right-handed projector acting on the renormalized fermion field F.
طبعا البروجيكتور هو الذي يعبر عن الخواص المغناطيسية، لأن فيه الجاما 5، والجاما 5 يعني تتعلق بالتي اي التي تعبر عن الباولي ماتريسيس. فالبروجيكتور هو الذي يعطينا أو يعبر عن الخواص المغناطيسية. وحتى الآن يعني أنا لم أعرف تعبير واضح له في الخواص المغناطيسية، لكن هو متعلق بالأبعاد x y z حسب الجاما 5، لأن الجاما 5 ترتبط بالجاما ميو اللي هي جاما ديراك، وجاما ديراك ترتبط بالباوليمتريسيس. كل هذه تتفاعل مع بعض البعض لتعطينا الجاما 5. إذا الجاما 5 تعبر عن المجالات المغناطيسية وهيئتها في الفضاء، وإذا عرفنا الجاما 5 وهيئة المجالات المغناطيسية في الفضاء يكون قد قطعنا حللنا لغز كبير جدا، ورسمنا خارطة لتشكيل المجالات المغناطيسية في الفضاء أو الجولون. طبعا المجال المغناطيسي يعني الجولون، وعرفنا أن كيف تتشكل الجولونز في الفضاء بين الكواركات، وكيف يحصل interactions بين هذه الجولونز.
And then can for all these square root of z, one would expand them as 1 plus 1/2 delta z. So that's all about the fermionic sector, and then we have finally the ghost sector. And here I will be a little bit scarce in information, but let's just say we use our psi gauge fixing. And then we have gauge fixing parameters psi and zeta. And for each vector boson, there is one psi and one zeta gauge fixing parameter, and they all transform with appropriate sect vectors. So psi v is given by z psi v times psi v bare on the left hand side. The same with zeta. Zeta v bare is given by z zeta v times zeta v. And then for the ghost fields, we have ghosts corresponding to each gauge boson. Ca Cz bare is given by a similar square root of Z matrix like the photon and Z fields. Z tilde, I will call it Ca Cz. And for C plus minus, there analogously Z tilde W C plus minus. And in the end, we will again be able to say that the gauge fixing does not renormalize, similar to QED, and for the exact same reason, because the gauge fixing is linear, or the gauge fixing function is linear in the quantum fields. Therefore, it is not there. It doesn't receive quantum corrections, and so it is not renormalized. But that implies that the ghost sector is renormalized in a particular way. So there will be again relationships between those renormalization constants for the gauge fixing parameters which derive from the non-renormalization of the gauge fixing term. But we will not explore this sector here in this lecture, at least probably not, because the renormalization of the ghost sector is only necessary if you want to compute unphysical green functions at the one loop level, or if you want to compute physical green functions at the two loop level. And potentially that is not something that we will do in this lecture this semester. All right, but in this way we have summarized the full renormalization transformation for the electroweak standard model. And the next step would be to work it out. In other words, this must be applied onto the Lagrangian. Then we obtain first the bare Lagrangian, including involving bare quantities. Then we can expand them according to renormalized quantities and renormalization constants. We will do the expansion to first order in the renormalization constants and obtain a one-loop counter-term Lagrangian, which gives counter-term Feynman rules. And so let us do that. And let's see, yeah. So, okay, let's first write this down. We do this transformation. L classical becomes L bare by applying the replacement, which is then re-expanded as the original L classical plus L counter term. And this can be done to first order in the deltas, which is sufficient for one loop level. For two loop level it wouldn't be sufficient, but for one loop level that is sufficient. And so in principle there will be a lot of counter term Feynman rules coming from that replacement, and it is not really possible to derive all of them in 1 hour. That just takes time and it is repetitive. Let's highlight a few counter term structure. So there will be counter terms for the vector boson self-energies. There will be counter terms for the Higgs or scalar self-energies. There will be an interesting counter term for the tadpole for a one-point function involving the Higgs. There will be counter terms for the interactions between gauge bosons and fermions. Counter terms for the interactions of Higgs boson with fermions, and counter terms for triple Higgs interactions, and many more. But at least these 6 different types of counter terms, they are all interesting for us, and all of them are interesting for the physics interpretation and also for understanding how in general this calculation works. And so I would like to at least derive parts of all of those 6 here, and then I think that is enough so that you really know how you could go on for everything else. And so in the end today I want to at least write down fully the counter term Feynman rules for such counter terms. In particular, just as a fun preliminary remark, so as one example, there would be something which you might not expect, for example, photon, neutrino. Photon, neutrino, neutrino counter term. So the photon will couple to the neutrinos via such a one loop counter term. How does that come about? That is one of the many things that we will derive. So just as an outlook, so that you see that there are some maybe not totally obvious things going on, half obvious. Therefore, let's do it. And yeah, let's see how far we get. So let us begin with the bilinear part of the vector boson self-energy. And so here the Lagrangian contains the following terms. And so we simply say the classical Lagrangian contains the following terms. It contains minus 1 over 2 field strength tensor for W plus minus, W plus mu nu, W minus mu nu, minus 1 over 4, then B mu nu, W3 mu nu times B mu nu, W3 mu nu. So here I already went halfway to the physical basis, okay, and but not quite. So you still see the original gauge structure where we would have a field strength tensor for the U1 gauge field, B mu nu times B mu nu, and we have field strength tensors for W1, 2, 3. W3 is here, and W1 and 2 are already combined to W plus minus. And so that could be equivalently written as the same thing, minus 1 over 4 times field strength tensors for the photon, A mu nu, Z mu nu, and A mu nu, Z mu nu. I write it already as a matrix notation, but this just means A mu nu times A mu nu plus Z mu nu times Z mu nu. And here we only need the bilinear terms. So the non-abelian parts of the field strength tensors are completely dropped because we are interested in the bilinear part of the Lagrangian, giving rise to such counter terms here. At this point we apply our renormalization transformation. And what does our renormalization transformation do to this Lagrangian? We would replace the W plus W minus by its bare version, which is square root of ZW times itself. So here we get a factor ZW in the front. And we already write that as 1 plus delta ZW over 2 times W plus mu nu, W minus mu nu. Okay, and then this is how the renormalization transformation works for that sector. Minus 1 over 4. And what happens here? Photon Z times photon Z, and the photon and Z transform with the square root of Z matrix. That is why I wrote it already like this. And so here that photon Z vector basically transforms exactly in the way like we see it in the first line, namely with this square root of Z matrix, which is written as you see on the right. And that thing transforms obviously with a transpose matrix. So therefore in the end, between the two vectors we obtain the sum of square root Z and square root of Z transpose. So let's write it, A mu nu, Z mu nu, and in between we have now the following matrix, unit matrix, plus 1/2, and then this delta Z AA, delta Z AZ, delta Z ZA, delta Z ZZ, plus the same thing transpose, plus 1/2 plus transpose times A mu nu, Z mu nu. So then we have it. So here this is now the renormalized form of this bilinear part containing the field strength tensors of the gauge fields, and from this you can derive counter-term Feynman rules, but this is the full Lagrangian. So for example, the photon times photon would be renormalized simply like 1 plus delta ZAA. The Z times Z term is renormalized with 1 plus delta ZZZ. diagonally, but there are mixing terms A times Z, which go with 1 plus delta Z ZA plus delta Z AZ. So there is a mixing going on. Then there are also the mass terms. So the classical Lagrangian also contains mass terms like these ones, namely plus mw square times w plus w minus plus 1/2 m, let's write it again like this, a z, then 0, 0, 0 mz square times az. These are the mass terms in the classical Lagrangian. What happens to those? So the mass term becomes mw square plus delta mw square times 1 plus delta zw times w plus w minus. Okay, so the mass becomes the bare mass and the w field becomes the bare w field, and therefore we have here a product of such renormalization transformations. And this product can then be expanded up to first order in the deltas. Then for the photon and Z field it becomes messy, plus 1/2. So, and now we have here photon Z as times, let me simply say, square root of this Z matrix transpose times this matrix 0, 0, 0 mz square plus delta mz square times square root of the Z matrix times az. And then we have here a product of 3 renormalization constants, and this product needs to be expanded up to first order. So maybe let's do that separately. What happens if we expand this product up to first order? So we obtain at 0th order, we simply have the Z factors are the unit matrix. Then we get just the original mass matrix, this mz square plus delta mz square. And then we have here one term plus 1/2 delta Z transpose times the original mass matrix plus 1/2 original mass matrix square times delta Z. And this delta Z stands for this matrix in the 2x2 matrix with the elements delta Z, AA, and so on. So, okay, and these terms in combination are exactly sufficient to read off such a counter term Feynman rule. So I would like to write down later on one blackboard all the counter term Feynman rules in a readable form. Therefore I would now not do the work of reading it off, but let us just practice. Can you read off such a counter term Feynman rule from the Lagrangian as it is written here? So let's practice briefly. So the counter term Feynman rule for this is the prefactor of the bilinear term of the Lagrangian, where derivatives become minus I times the incoming momentum. So for example, for the WW term, we have here something that is the field strength tensor. We have seen that before, so that gives the transverse projection operator, so that gives in momentum space g mu nu p square minus p mu p nu, transverse object, and then the counter term Feynman rule would be that object times delta zw. And from here we get on the one hand delta mw square plus mw times delta z, and that is multiplied with g mu, the metric tensor. And then our counter term Feynman rule would be this term plus the other term. And that is the thing that I will write down later on onto the blackboard, and that can be read off here from this Lagrangian. And for the photon and Z, it's way more complicated, but you can also see how it works. So for example, for the photon and Z, we get a matrix-like structure here. So for example, in the kinetic term, we again get here p squared g mu minus p mu p nu from these field strength tensors, and then this would be multiplied with the appropriate matrix element delta z AA or delta z AZ, delta z ZZ, depending on which combination of fields we will look at. So here we will have AA or AZ or ZZ, and each of these combinations will be multiplied with the appropriate combination of elements of this matrix, and then each of them will also be multiplied with something from the mass. So the ZZ part will get this mass counter term delta mz squared, and the photon will get 0 here, and then there are off-diagonal elements coming from this product of delta z transpose times this matrix. However, this gives only something in the second column of the counter term mass matrix, and this gives only something in the second row of the mass matrix. And so in the 1, 1 entry of the mass matrix there will be no mass counter term, but in all the other entries there will be mass counter terms. So this is the thing we will write down later on, but I will not do any more intermediate derivations unless you want me to. Do you want more details on this? As a no. Okay. Then that is done. So this is the counter term Lagrangian. So from this we would get counter term for the vectors in bilinear form. Next, bilinear terms for the fermions. Here the Lagrangian contains fermion f bar times I d slash minus mf times f. It's really as simple as that. That is exactly as in QED. However, the renormalization transformation is not as in QED because the left and right-handed fermions transform independently, and so that becomes the following: f bar times here the bar exchanges the role of left and right, so PR times square root of ZFL plus PL square root of ZFR times I d slash minus MF minus delta MF, and then once again times P left square root of ZFL plus P right square root of ZF right times the fermion field. And that can now be simplified by doing the gamma algebra. So then we have f bar times the following, let's say I d slash times what? I d slash is multiplied as follows. So if we anti-commute gamma 5 with d slash, it gets minus gamma 5. So we can anti-commute the projection operators with the d slash. Then they reverse their meaning and they combine with those projection operators, and then we see that left just obtains square root of z left times itself. That gives just ZFL without square root. And for the right-handed, the same, P right times ZF right. So in the kinetic term with the d slash, simply the left-handed field and the right-handed field appear independently, and they each get just renormalized with an independent z vector. Then how about the mass term? So minus mf, and so the mass term gets now multiplied as follows. So there is one term with p left times square root of zf left times square root of ZF right. Okay. So we get this product ZF right times ZF left for the left-handed, and actually also for the right-handed, so the P left drops out, and we simply get the mass times this minus delta MF, and here I drop the field renormalization because we work in first order. So then, from this here in this case, let's make explicit the counter term Lagrangian for the bilinear parts of the fermions. That would now be exactly the delta part of this Lagrangian, and that is here f bar times I d slash times p left delta set f left plus p right delta set f right times f minus f bar times delta mf plus mf times delta 1/2 delta set f left plus delta set f right. That is the counter term Lagrangian, evaluated precisely to first order in the deltas. And let me make a footnote here. We have assumed CP conservation and real renormalization constants. In principle, one could also wonder whether the Z factors might be complex. Then in this case here on the left, where f bar renormalized, we would get the complex conjugates of the Z factors, and they would not be the same as the original Z factors, and then here in these sums there would be conjugation, and the p left, p right would not completely drop out. So that would be a complication that is necessary in the case of CP violation. But let us not discuss that here, but let's keep it in mind, because maybe some of you might work with CP violation later on, and then this might have to be generalized. So, but that is the fermion part, which is maybe the simplest, and from this we can also immediately read off the counter term Feynman rules. So you can already work on the next part, which is the Higgs. So next we would do the Higgs, and there let's renormalize the Higgs potential, which contains the tedpole term and the bilinear term, and maybe let's even immediately do also the trilinear term for the triple Higgs interaction. So you can take the Higgs potential from the last lecture and apply the renormalization transformation to it. In the standard model, yes, and allow for CP violation that the CKM matrix is complex, and then there is no reason anymore why the Z factors might be real, so they might be complex, or one might have to allow for complex renormalization of the Yukawa couplings, and so there are different ways to parameterize the counter term and the bare Lagrangian, but somewhere there must be complex renormalization constants. It is exactly the same kind of analysis that one has to do as we do at tree level when we introduce the CKM matrix in the first place, where we ask ourselves how many independent complex phases are inside of the CKM matrix. One would have to do exactly the same discussion at the level of the bare Lagrangian, and you only know the bare Lagrangian first of all must be general. You have to write down all terms, including complex terms, which are compatible with gauge invariance. But once you have written down all terms, you can, as in the tree level case, absorb as many phases as you possibly can without loss of generality. And then you can do it in different ways, but you can figure out what is the necessary set of complex renormalization constants. Then, for example, you would see that if you do this with complex Z factors, then nevertheless, in the case of the d slash term, in the d slash term there would always be automatically a product of z star times z, and therefore here only the real part of the set enters and complex terms cannot enter at all, they drop out immediately. But in the mass term that is not the case. And so, but there you would then have somehow an ambiguity or different options of either absorbing the complex parameter inside of some delta m or generalized mass counter term or inside of the field renormalization constants. And such discussions are of interest in the standard model CKM renormalization, but also, or maybe even more so in physics beyond the standard model, where these things happen in more elaborate forms. And these are probably some items which I would leave for the future, and maybe this is something that is more appropriate in the actual research work, but a little bit beyond the lecture which we do in this semester. Oh, but at least we will cover here the renormalization of the standard model without CP violation and with one generation. But there are, let me just say this, I mean, so that it is on the record. And so here, if you have many fermion generations, then you would have Fi. I runs from 1 to 3, for example, and then these set factors would be matrices in this 3 by 3 space of generations. And then you would also have mixing between the generations, and the muon or up quark could mix with the top quark and so on via these set factors. And then you have lots of ambiguities of how to define the set factors, and that is a quite, let's say, involved issue. And so we don't, at least I do not plan to do it, but you already see this matrix valued renormalization between the photon and Z. And for the fermions, it would probably be still a little bit more complicated than for photon and Z, but similar. Let us continue. So the scalar Lagrangian contains the following: plus tadpole times h plus tadpole divided by v times 1/2 Goldstone 0 square plus charged Goldstone absolute value square minus mh square over 2 h square minus lambda v h cube plus and so on, plus other terms. But these terms are definitely there, we have derived them, and so now let us apply the renormalization transformation. So that becomes tadpole t plus delta t times 1 plus 1/2 delta zh times the Higgs field. Okay? So two renormalizations, and that will be expanded up to first order in the deltas. Then next, t plus delta t divided by v plus delta v times here z g0 times 1/2 g0 square plus z g plus minus times g plus square minus mh square plus delta mh square over 2 times zh times h square and minus lambda plus delta lambda times v plus delta v times zh to the power 3 over 2 times h cube. So, and so on. So actually, here I used some abbreviations, namely the V, which appears here, shouldn't actually appear because we forced ourselves to write the entire Lagrangian in terms of only physical parameters. So what does it mean if I write V? V only appears in the sense of an abbreviation of some combination of the more physical parameters. So V is an abbreviation for 2 times the W mass times the weak mixing angle SW divided by the electron charge. And the SW itself is also an abbreviation for 1 minus mW square over mz square, because only mW and mz and E are fundamental parameters. Everything else is just an abbreviation for those more complicated formulas. And similarly, lambda is an abbreviation for mx square times V plus tadpole divided by 2V cube. And here you would then have to plug in V, which is that, and then lambda becomes an incredibly messy expression. But that is what it is. And so we have to view those parameters here as abbreviations for those combinations, and for those combinations we have defined how they transform under the renormalization transformation. Therefore, we know exactly what delta lambda is. Delta lambda is the variation of this expression given the transformation of the Higgs mass and the tadpole and so on. So let us evaluate this for the case where the original tadpole is actually 0. So at 3 level we have found the correct minimum of the Higgs potential, and then we evaluate the counter term Lagrangian around that. So we set the original t to 0, but we do not set delta t to 0. But if we do that and expand to first order, then we get a simplification. So here delta t is first order, t is 0, and then everything else here doesn't matter. So we get here simply delta t times h. And here also delta t divided by the 3 level V is all that we need. And the set factors also do not contribute at 1 loop level, so we simply get that. And that is then our mass counter term for the Goldstone bosons. And for the Higgs mass, it behaves essentially in the normal way. So we get delta mh square plus mh square times delta zh divided by 2 times the Higgs field square. And here we would get minus, okay, let's keep the abbreviations, V times delta lambda plus lambda times delta V plus V times lambda times 3 over 2 delta zh times h cube. This is our counter term Lagrangian for the Higgs potential sector. And I do not write down what delta lambda is, but delta lambda is unambiguously defined by saying this line before. So it is clear, right, what you would need to do in order to evaluate delta lambda. Maybe let's do here an intermediate important remark. So we see this here, other quantities must be regarded as abbreviations. So let's say most importantly, let us write down some important abbreviations. So let me maybe copy that from the left. So the most important quantity for sure is the weak mixing angle SW. SW, let's say SW square, is defined as 1 minus MW square over MZ square, and that is also the same as 1 minus CW square. So these quantities are super important quantities, but they only appear in the on-shell formalism as abbreviations for this fundamental expression. Similarly, let me also write down again the vacuum expectation value. V is given by 2 MW times SW divided by E. And maybe also as a third interesting thing, the gauge coupling GW would be an abbreviation for E divided by SW. And so then, of course, it is allowed to write your Lagrangian in terms of those expressions, but they should be viewed as abbreviations for this. And now what happens if you do a renormalization transformation? So for example, delta SW square. What is now the renormalization transformation of SW? It is, of course, the delta variation of this object. So it is delta minus delta of this fraction MW square over MZ square, and that is evaluated in the sense of infinitesimals or derivatives. So that is basically minus delta MW square divided by MZ square plus MW square delta MZ square divided by MZ to the fourth, and that can actually be nicely written as minus MW square over MZ square times then the following, delta MW square divided by MW square minus delta MZ square divided by MZ square. So it's like here this prefactor times the relative variations of the W and the Z boson mass plus delta square terms. So this is a one loop expression. So but then delta SW square might also be an interesting building block which can appear in the counter term Lagrangian, but whenever it appears it is really meant as an abbreviation of that longer expression. But it's clearly a useful thing because it will often appear. For example, then if you happen to have the weak gauge coupling GW entering somewhere, then it might be simply useful to write down the variation of this, which would be delta E divided by SW minus E divided by SW times delta SW divided by SW, and then delta SW is that. And then you know how the gauge coupling GW transforms under our renormalization transformation that we have defined. And so that are all useful building blocks that you can make use of in practical calculations. And last, let's also record delta V. So delta V is this the differential of this fraction, and that is simply, let's say, V itself, which is that. And then you do the relative variations of all the quantities, so delta MW over MW plus delta SW divided by SW minus delta E divided by E. That would be a relationship for delta V, and that again is something that can come in useful for abbreviating counter-term Feynman rules, for example, as you see here. And you could go on and do the same for lambda and for other quantities of interest. But mainly it is important to understand that there are fundamental quantities, namely exactly for example, in the bosonic sector, these 5 quantities that we have defined, and we have 5 fundamental renormalization constants, and everything else can be computed out of those 5. And that is what is exemplified here. Let us Let us go on. Actually, maybe let me ask you, I mean, how much more do you want to see of that kind? Yeah, question?
So to now, when we normalize, I have seen these deltas as they are the counter terms, and they are infinite, for example. And how can I now imagine, now see this? For me, now it seems like there will be, for these abbreviations, like a total derivative. How do I imagine this? Why are these?
It is of one loop order. So the ordering principle is 3-level, 1 loop, 2 loop, and that is a perturbative ordering principle. And so we use formal perturbation theory in the sense that we assign strictly an order to each expression, strictly an order in perturbation theory or in terms of loop numbers. And so all the delta quantities for us are now of 1 loop order. And so they are infinitesimal by definition compared to the 3-level quantities like MW over MZ. In the sense of 1 over epsilon, they would diverge, but in the sense of this loop counting, they are infinitesimal, they are strictly of 1 loop order, and that is the ordering principle that we apply here. And that is this renormalized perturbation theory, where you sort according to the number of loops, and then you have 3-level Feynman diagrams where all the couplings, all the ingredients of the diagrams are of 3-level order. You have 1-loop Feynman diagrams, and you have 1-loop renormalization constants, and they combined give you a full 1-loop correction. The 1 over epsilons cancel, and then after that cancellation, indeed, the total 1-loop correction is indeed numerically small. Doesn't depend on epsilon anymore and is numerically small, but before the cancellation of 1 over epsilon, we order strictly according to the number of loops. And that would also apply to higher orders when we would take into account delta square terms. I mean, here, everywhere there would be delta square terms appearing from such a variation here. And those would then be of 2-loop order or of even higher order. And they would be combined with actual 2-loop calculations of 2-loop Feynman diagrams, and then again the same thing will happen. So, you know, I told you, for example, that there will be now a counter term photon neutrino. Where does that come from? We could also go through the calculation of this, but actually I have the feeling that we should maybe just write down the counter term Feynman rules and then we discuss them a little bit. And the derivation in all cases is analogous to this one. Okay. Is that sufficient? Maybe let's see how it looks like, and if you need some more explanations, then we can add them afterwards. So let me clean, and then let's really write down systematically the counter term Feynman rules. So let's write down this counter term Feynman rule between 2 vector bosons V and V prime with Lorentz index mu nu and momentum q flowing through the Feynman rule. And I still kept the Lagrangian here. So I told you that we get from the kinetic term minus I times this transverse building block g mu q square minus q mu q nu, and that comes with what? Field renormalization constant. So where is it? Here. So that combination here produces exactly this operator, and that in the counter term Lagrangian is multiplied with delta zw. So for ww we get here delta zw. For photon we get 1/2 delta ZAA plus again 1/2 delta ZAA, so we get delta ZAA. For ZZ, we get delta ZZZ. So in principle, we always, for the diagonal ones, we get the appropriate diagonal field renormalization constants. What happens for a photon Z? For photon Z, we get here the combination of diagonal terms, 1/2 delta ZZA plus 1/2 delta ZAZ. And therefore, in general, we can say delta Z V prime plus delta Z V prime V divided by 2, and that is always correct. And of course, for the W case, you should interpret WW equal to delta ZW. Then from the mass, we get the following, plus I over 2 times mv square times delta Z V prime plus mv prime square delta Z V prime V times G mu nu plus I delta mv square Kronecker delta V prime. Okay, let's start explaining the last term with the Kronecker delta. So if we have diagonal self-energy, WW for example, WW, then we simply get from the top line the mass counter term delta MW square plus delta ZW times the original MW. And so then for WW, this just produces MW square times delta ZW. Okay. For the diagonal Z, we would get from here delta MZ square times times 1, and from here we would get MZ square times delta ZZZ. That here produces MZ square times delta ZZZ, the diagonal Z vectors. What do we get for the diagonal photon self-energy? Photon. What is the mass counter term coming into play for photon? So from here we get 0. So for photon we get 0. There is no delta M photon. That is 0. But from the mixing terms, for the photon we have to look at this matrix entry coming out of that matrix product. That matrix product in the left upper corner produces a 0, and this matrix product also produces a 0 in the left upper corner. So therefore for the photon we get 0. And indeed, if you plug in AA for the two indices, you have here photon mass which is 0, photon mass which is 0. So for the photon diagonal counter term we get absolutely no mass counter term. The photon receives no mass counter term. But the mixing photon Z, that receives something, and it comes not from the explicit delta MZ, but it comes from the product here of the matrices. And from this product, let's start with this. So from this product you get in the off diagonal entry something mz square times delta ZA, which is not 0 in the off diagonal, and here you get delta ZAZ times mz square. So therefore here you get mz square times delta Z ZA, and here you get mz square times delta Z ZA, which is actually the same. Okay, so it works in all cases. So let me maybe highlight this in particular. AZ, which is the least obvious one, would give you minus I G mu nu Q square minus Q mu Q nu times delta Z ZA plus delta Z AZ. The two are different, and from here plus I over 2 mz square delta Z ZA times G mu nu. So from the matrix, maybe I said it incorrectly, but because of the transpose, both matrix products only give rise to the same entry delta ZZA, but not to the other one. So here you see that they appear in an unsymmetric form. So this matrix element delta ZZA, that always has the following role. You see in the renormalization transformation, this appears in a place where the bare Z field gets a contribution from the photon. So here you get a term in the Lagrangian which involves the photon field, but the photon field appears in a place where actually the Z boson should appear. And that is why here the photon gets multiplied with the Z boson mass square. That is the interpretation. Delta ZZA makes the photon behave like the Z. And the other one, delta ZAZ, does the opposite. The fermion counter term, FF, is simpler. I times P slash delta ZFL times PL plus delta ZFR times PR minus I times delta MF minus MF delta ZFL plus delta ZFR divided by 2. This is directly to be read off from our Lagrangian. Then the scalar self-energy SS, there are only diagonal scalar self-energy counter terms. There is no mixing. For example, neutral Higgs, neutral Goldstone, that mixing doesn't appear. And for the diagonal parts, we get the following: I times P square delta ZS from the kinetic terms, which we have not even written down because it's too obvious. And then for the mass, we get minus I times the following. In the case of the actual physical Higgs, we have delta M Higgs square plus M Higgs square times delta Z Higgs. And for the Goldstones, we do not have zero, even though the Goldstones are would-be massless, would-be Goldstone bosons. But we do not get a zero counter term, but instead we get minus delta tadpole divided by the vacuum expectation value. And so that is what we have seen just in the discussion of the Higgs potential. Then there is the tadpole counter term for the Higgs, physical Higgs ending in a one-point function. That counter term is I times delta T. And so here there is a relationship between the Goldstone mass and the tadpole, and so they have the same renormalization constant. And the claim would be that if that divergence of the tadpole is cancelled by delta T, then automatically also the Goldstone divergence in the mass is cancelled as well with the same renormalization constant. So there is an interrelation between the divergences. Then let me add also the triple Higgs counter term. The triple Higgs counter term, Higgs, 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 that comes from this term in the Higgs potential, which we have not fully worked out. But you remember that there was this term lambda times V times H cube. That is what we wrote down. And I told you that lambda and V need to be replaced by those longer expressions, and they need to be renormalized. And let me now write down the result that comes out of that little calculation. Minus I times mh square times E divided by 4 mw times SW. That prefactor is what you obtain if you plug in lambda times V. And then there appears now a symmetry factor times 6. This is the usual 3 factorial coming from the permutations of the 3 Higgses. So I write that explicitly, and that would of course cancel 3 over 2, but let's keep that explicit form. And then you get the combination of renormalization constants from doing what I told you, and I write down the result. mh square, delta mh square over mh square, plus delta E over E, minus delta MW over MW, And so far this is very understandable because it directly corresponds to the renormalization of that fraction. Each term gets renormalized in this infinitesimal way. Then it goes on minus delta SW divided by SW, that is also understandable. Then there comes plus 3 over 2 times delta ZH. That is hopefully also understandable because we had the factor square root of ZH to the power 3 and the variation is 3 over 2 delta ZH. And then there comes the contribution from the tadpole, which you need to work out. That is delta T times E divided by 2 mH square MW SW. And so you saw from the lambda and V formulas there was a tadpole appearing, and if you take into account that tadpole, renormalize it, then that enters the contribution in exactly this way. So it's a kind of quite lengthy form for this counter term finding rule, but that's what it is. And so you could now introduce abbreviations like delta lambda, delta V, as I have said before, but here I chose now to really write it absolutely explicitly in terms of our fundamental parameters and renormalization constants. Now, let us come to the interactions. Do you first have any questions to this? This is what we can basically read off from our Lagrangian. And you should be able to do the calculation with all details. We have sketched how it works, but we have not really evaluated all details. But let us now come to the interactions. So for example, photon and fermion-fermion interaction. What is the counter term for that? And so in one way it is obvious because you take the original Lagrangian term minus IEQF, and then you renormalize it in the obvious way. Clearly you get delta E over E, and clearly you get something from the photon field renormalization delta ZAA, and that is also what we have obtained in QED. But then we obtain the field renormalization for the fermions, and that is now distinguishing between left and right. So we get plus delta Z FL times P left plus delta Z FR times P right. Because the left and right-handed fermions fields renormalize independently. That is the renormalization of the photon cell interaction, and now it goes on because the photon and Z mix. There is now a term where basically you get something times the mixing delta Z ZA. And again I say you get from the bare Lagrangian the Z boson appears in bare form, and the bare Z is replaced by delta Z ZA times the photon field. So the photon, renormalized photon, gets a contribution in the counter term coming from the Z boson interaction. So this renormalization constant gets multiplied with the 3-level Z boson vertex. Let me write down the value of the 3-level Z boson vertex. This is minus IE divided by 2 SW CW gamma mu. Oh, I forgot gamma mu. Sorry about this. Gamma mu, please. Times this CFL PL plus CFR PR, where we have introduced the CL, CR constants. These are just quantum numbers like hypercharge and isospin and so on, which govern the Z boson interactions. But this is literally the 3-level Z boson interaction with fermions, and that is multiplied with delta ZZA, and in this way it contributes to the photon counter term. And now you see the answer. Why is there a counter term photon neutrino? Because the Z boson couples to the neutrino in some way, and that is multiplied with delta ZZA and contributes to the photon. That is even divergent, and it is necessary to cancel divergences from loop Feynman diagrams with that form. And similarly, let me also write down the counterpart for the set mu interaction with fermions that behaves in the opposite way. So you get the tree-level set vertex times many renormalization constants plus the tree-level photon vertex times the opposite delta z a z from the same effect. So actually let me start with this. So minus I eq gamma mu times delta z a z. So this is exactly the same logic as here, and you get the photon tree-level vertex times this renormalization constant contributes to the Z interaction. So that is simple, and then the rest is much more complicated. So minus I E divided by 2 SW CW times gamma mu, and now you get the renormalization of all of this. So we get delta E over E minus delta SW over SW minus delta CW over CW plus delta Z ZZ over 2, then plus delta Z FL times P left plus delta Z FR times P right, and all of that is multiplied with the tree-level coupling combination CFL P left plus CFR P right. That's it. So this is now in hopefully readable form the structure of counter terms, and in this way one could go on for a while and derive the complete list of all counter term Feynman rules. And there are many more, of course, like Higgs fermion interactions, triple gauge boson interactions, quartic interactions between the Higgs and the gauge bosons, and so there are many more terms, but the logic is then becoming similar, and I hope you understand how one can in principle derive them all. And I already gave you the literature references where you can find the complete lists. Also, you can see that the entire approach is quite algorithmic. Therefore, it is really possible to implement even the renormalization transformation in a computer algebra program and write a program that gives you the counter term Lagrangian. Now, let me add to this a small list of important green functions. So we would now have things like renormalized vector boson self-energy at the one-loop level, which we denote like in QED, sigma hat VV prime mu nu of Q, which is then equal to minus I sigma without hat mu nu VV prime of Q plus the counter term Feynman rule, which I simply write like this. Okay, and then you could copy the expression from there and put it here, and then you know how you obtain from the unrenormalized self-energy the renormalized one. And this object is the one particle irreducible one loop contribution to this green function. Similarly for the fermions, FF hat of P is equal to the unrenormalized self-energy plus this counter term Feynman rule, and for the scalar as well. And for the tadpole, we have I times T hat, which doesn't depend on momentum, which is this one particle irreducible green function with one external Higgs, and that is the unrenormalized. So no counter terms plus I times delta t. And finally, minus I times lambda hat, 3-point function for a fermion, is defined like in QED as the one particle irreducible photon fermion fermion. 3-point function is the unrenormalized version lambda hat f plus the counter term Feynman rule that we have written down before. And then you know that the counter terms and the renormalization constants, all the delta c, delta m's and so on, they appear in a known way in these one loop building blocks. And later on we will impose renormalization conditions, like on-shell renormalization conditions, such that some self-energies vanish at specific momenta, and then those equations can be solved in a well-defined way for the renormalization constants. So let me highlight a few things. So here there is a difference to QED. There is no EQ prefactor as in QED. So the definition is a little bit different because the EQ prefactor is not so helpful here because we have this mixing between the photon and the Z boson prefactors, and therefore we omit it here. And then there is also a kind of interest in the standard model to have full one particle irreducible objects, including tree level. We also didn't have them in QED and counter terms as well. So let me give some names. So I times gamma VV prime mu nu. So gamma instead of sigma. The difference is all of the gammas. So let's start with this. So here some of them have a minus in front, which is motivated by the explicit Feynman rules, which we know also have a minus and so on. And then we have specific names for the different green functions. Now all 1pi objects are defined with plus I gamma in front, and they involve tree level and all the necessary loop corrections. So that would be given by this tree level term coming from the Lagrangian minus I times sigma hat mu nu VV prime and so on. I times gamma FF would be given by this tree level term plus I sigma hat FF and so on. I gamma S is analogous, I hope. And also I gamma H is given by I times T hat plus I times the tree level tadpole I times T, which we usually set to 0. And then finally I times gamma AFF is the 3-point function mu, is given by the tree level photon fermion fermion vertex, which is the tree level 1pi contribution minus I times this lambda hat mu f. Okay. So these are then full building blocks including tree level, and it might be useful to write down conditions for those where the tree level parts are included, because then it's maybe nicer to write down all order equations for those gammas as opposed to imposing something directly on the one loop building blocks. I think now time is up. Maybe you have some questions to the procedure. Otherwise, I can give some comments. So the next step would be, of course, to write down the renormalization conditions. We have now a setup which is developed. We could write a computer program to give us all the counter term Feynman rules and do all the derivations. We can discuss here for many green functions the counter term contributions. We can check, we can compute green functions, check whether they can become finite and so on. But the next step in our general procedure, also following the QED example, is to set up a renormalization scheme. We will really define systematically what we want from the finite parts of our renormalization constants. And there, as we discussed, we will choose the on-shell scheme, which is a very, very advantageous scheme for the electroweak standard model, like for QED. And there we will impose certain conditions on exactly these objects that I've listed here. In essence, we impose that the finite parts and also the divergence parts vanish at on-shell momenta. And that will fix the finite parts of all renormalization constants, and it will have a very definite and, let's say, direct physical interpretation, which is essentially identical to the interpretation in QED. But there are quite a few more comments to be made to the on-shell renormalization conditions compared to QED, and so we will take our time to write them down and interpret them and give some further comments, and so we will do that next time instead of rushing it today. Okay, so if you have no questions, then I would stop here, and thanks, and see you in the afternoon for the exercise.